Hello ladies and gentlemen, you're looking at a magnetosphere simulation looking down on the solar system, and you see a CME, a coronal mass ejection, coming through. Now this happened a week or two ago, and the reason I'm showing it to you again is that I want to impose upon you how particles of hydrogen and helium end up compressing our magnetosphere and creating like a crease or an indentation, and that when it comes through, that comes through quickly. It's not sustained. So any anomalies that we see in our magnetosphere that are sustained can't be a coronal mass ejection. And the reason I'm showing this is because there's been so few of them coming through, and it's pretty cool to watch the impact that they have upon those vectors. I'm straightening them out. But notice deep in the tail stream, you still have vectors pointing at Earth, pointing from left to right. And the solar wind, if the sun's off to the right, should be going from right to left. So if we were passing in between the sun and the brown dwarf, you should see some wind coming in to Earth up that tail stream and creating opposition. And that's what we have seen. Now, our magnetosphere has been a mess. It's been a constant mess. It's been a hot mess, and it has not been due to CMEs. You can see here, CMEs wreck your X component and your Z component and your Y components of your magnetosphere. They cross them over. We have geomagnetic storms. There's twisting of the magnetic field lines, which creates geomagnetic storms. But what we're talking about is something that's been sustained, and that's been the arrival of electrons. This electron simulation shows you how these electrons, because of their magnetism, can warp and shift and change the shape of your magnetic field around Earth. Generally, the more you get, the more expanded the magnetic field should be, unless of course the Earth is sandwiched in between two objects that are creating compressions both on the front side, which is the right, and the back side, which is the left. And you can see our magnetosphere at times has been getting compressed down to almost geosynchronous orbit. Now since it has expanded, a coronal hole stream, I do believe, may have come through here, but that raises even more questions because we're not seeing coronal holes per se that are on the equator at all times, but at all times we're seeing this kind of influence and even a total saturation of our magnetic field with electrons. That will spike your background radiation. We go to the L belt, which is a radiation belt above the Earth. We look at these because sometimes the electron simulations are suspect. They sometimes don't match the NOAA report, but we always go to this and find high density electrons are always there. So if a brown dwarf was in our solar system, the amount of helium would increase in our solar system because brown dwarfs consist of helium, lithium, some heavier elements, trace elements, but tons of electrons. There are electron magnets, and hence they shoot out electron jets. The magnetics on a brown dwarf are so chaotic that they constantly are setting off static electrical discharges all over the surface plasma, injecting them out into space in all directions, roughly leaving the surface of the brown dwarf at approximately 10,000 degrees Kelvin. But so if you were trying to hide the fact this brown dwarf was in the solar system, then anything that measures helium or lithium should be redacted or changed, smoothed out, altered, censored, what have you. Well, this is an instrument that measures helium. And notice it dates back to 2018. When you go to the archives and try to compare what this stuff used to look like, around the sun, the helium signature around the sun, it gets very hard to do so when there are so many redacted files. And those little pink X's are empty files. So you have a telescope that's, you throw a filter on it, you snap a picture, and that's how easy it is to monitor the helium on the sun. And if there was a brown dwarf in the solar system, you think that would become one of the more prioritized instruments, but instead of being prioritized, it's being sanitized. And you see complete absence of data. Thank you, Mauna Loa. And yes, Mauna Loa has several dead astronomers. Yes, be careful when you're on the street. You can get run over if you're an astronomer at Mauna Loa. One of the other instruments that was so instrumental in telling us what was going on with the solar system was Ulysses. Ulysses is orbiting the sun and the north-south portions of the sun, measuring the coronal hole streams coming in and out, but also measuring equatorial stuff, and they're picking up all kinds of new particles. And it was Ulysses who put a rubber stamp on this solar wind. It was Ulysses who confirmed there was incoming and outgoing, that there was an actual upstream and a downstream, and told us the temperature, the speed, everything we wanted to know about this second source of wind, the second sun. Well, in 2013, even though you and I paid for this data, 2013, much like Mauna Loa, 2013, Ulysses decided not to show you any more measurements. So the density of that interstellar medium we know has been increasing, but we can't prove it by using that which we paid for to use in the first place. I call all that taxation without representation is what I call it. Now, when we pass in between a large object or a 90 degree to the sun and Earth, when something's direct opposition to Earth and Sun, or 90 degrees to the Earth and Sun, we get the mid-Atlantic ridge shifts. The entire ridge from north to south shifts. And many of our volcanic regions become more active in terms of seismicity. So I said, if we're going to pass in between, to look for the mid-Atlantic ridge to shift. I said clearly, you're looking at roughly 5 pointers, about 10 kilometers deep, and most of those are 5 pointers. But off the coast of Africa, they had a large 6-pointer there off the mid-Atlantic ridge. Now, that could have signified the middle, the start of an alignment. Also, I want you to look at the bottom of this map. If you notice, the whole Antarctic ridge shifted as well. That's a horizontal plate. So we had a vertical plate that shifted, that normally is quite shifty, comes and goes. But the South Antarctic plate, that one that goes around the Antarctica, generally is kind of a quiet zone. There's not a whole lot going on down there, and when you see that whole southern horizontal plate, that fault line moving, that usually indicates a wobble. So then we go and look at the north to see if we can get some earthquakes at the far north, because if the Earth is bouncing up and down like a yo-yo, any horizontal plates at the top would be responding similar to the Antarctic plate. And we don't quite see the same stuff going on in the north as we have in the past. We don't see the same patterns as we have in the past, but we do see bizarre quakes at the top of the globe that normally we do not see. And these are occurring, most of these are occurring in the water, so we know we're not looking at calving events where ice breaks off and gets recorded on a seismogram. So that's loosely connected, that the Earth could be bouncing up and down. Now, just in the last week, we look at the Mid-Atlantic Ridge. The previous was about 3 weeks of the Mid-Atlantic Ridge, just in the last week. So we have, over the course of 1 month, the entire Mid-Atlantic Ridge shifting. And indeed, in the last week, you can see the earthquake sequences are very evenly spaced, and the magnitudes are very even, and the depths are very consistent at 10 kilometers depth. So wait a minute. That means that this ridge is being subjected to a general force and the same force. And generally, motion, the law of motion, is very consistent overall force that would apply to the entire Mid-Atlantic Ridge if, in fact, Earth wobbles or gets bumped a little bit. Now, the ridge crest quake sequence, we broke all kinds of California records with thousands and thousands and thousands of quakes. They just did not stop for an entire month after the ridge crest big quake. We've had that whole area has just been moving and shifting, and just this last week, they've tapered off, completely tapered off to just a few dozen quakes instead of hundreds and thousands. So yeah, we could have passed in between. We told you the solar wind would not be getting any faster than almost a classic typical signature that we see on these graphs. You notice the orange line density runs opposite of the yellow line. That's been what's been the case for 30, 40 years, where the thinner the particles, the faster they run, and we've seen a complete variation and a divergence from that. We were seeing speed and density increasing at the same time. That can only be caused by a second source of particles elevating your density. When they run in roughly the same direction as the sun's particles, then you don't get a decrease in speed with the density. So that's why the density versus speed vectors have been thrown off. But this is a classic presentation of what it should look like. But no sooner did we say the wind isn't going to get faster than 550, did we get hit with a 650 mile per hour, or kilometer per second, coronal hole stream. But since that time, look what's happened to the speed. It's just tracked down, 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 down. And today we see the slowest wind we've seen probably. I can't imagine the solar wind getting any slower, down to 200 kilometers a second. Are you kidding me? And look at the temperature. Basically, you're seeing very cold particle temperatures in a relative sense. And those temperatures in the green actually match what Ulysses is measuring and was measuring, the cosmic wind, this interstellar wind, roughly the same temperature. So we're measuring a second wind. When they run opposition, there's no speed. We can't mess up our magnetic field the way that we need to create geomagnetic storms. So you can see how flat those have gone. Now, when we took a snapshot of a magnetosphere compression that happened a few years ago, this was almost down to geosynchronous orbit. This is about 7-8 Earth radii the magnetosphere is sitting at. So we have particles coming through, compressing the magnetosphere, but look at the backside. Look at the tail stream of Earth. We don't see any energy back there, but now compare to today, where we have a constant supply of energy. We have frequently more than one bow shock zone out front. That's the right hand side. We see expansions followed by compressions, followed by expansions, almost harmonic at times, as our magnetosphere fills with electrons, ejects those electrons without any coronal hole streams, and then it collapses a little bit and then refills, and the more electrons you get into your magnetic field, the more they repel one another, the wider your magnetic field expands. But then when particles come through, you get a compression. But immediately, even if CME washes out those electrons, my goodness, how quickly that energy returns on the left-hand side of the simulation. And we've been tracking this for you for over 2 years, and anybody who's watched this channel knows that left-hand side has been increasing in energy. And now it's constant. It's not going away. So if we're passing in between a brown dwarf and the sun, this is the kind of stuff you would predict you would see. And what a far cry and a new normal that has become, because we're able to go back and compare. Now we look at the Enlil spiral, the Enlil spiral, The Enlil spiral shows CME slapping Earth. The thing about this CME that's really curious is it gains in density. It becomes red as it passes Earth and gets further away from the sun. This is supposed to be like a shotgun. The pellets are supposed to scatter. The only thing that could cause a CME to increase in density is to run into a second wave of particles. When an outgoing wave in the ocean runs into an incoming wave in the ocean, that wave doesn't cancel out. It actually doubles in amplitude. Just because they're traveling in opposite directions doesn't mean anything. And then when we look at that middle pie cut, there's a constant swirling of energy. Some of them are elongated and not even perpendicular to the plane of the solar system. They're actually, in the same line of the solar system. And then when you go to the far right, you see a constant presence of that light blue shifting on and off, flickering on and off, fluxing constantly. And we're not seeing any coronal holes on the sun to be creating this. So basically what you have is a very weak sun running into waves. You have outgoing waves in this ocean and incoming waves, and Earth is in the middle of it. And you get to see how slow some of these CMEs actually travel away from the sun now, because they're meeting opposition, but how they become dense, more dense, the further away they get. This would take physics and throw it out the window, but we know you can't do that, so there has to be an explanation, and the most logical explanation is those waves leaving the sun are running into waves of particles coming into the sun. So, and this is what we're happening, that segmented, repetitive, harmonic signature that we see on that rectangle on the Enlil, that right hand side. This is what's happening. You have spiral wind coming out, and imagine wind coming in, let's say from the lower right or just from the right. You can see those spirals kind of slap against the incoming wind and create fluxing and crossing of magnetic fields. But when those particles get in between those spirals, the darker blue represented here, and you can see when they get in between, they'll accelerate because they've kind of dodged or squeaked by the wave of particles coming from the sun. They get into this void and they get accelerated. Look at the dark lines, the straight lines. Those are direction of magnetic field lines. Look how some of them are absolutely perpendicular to the sun, but only on one side. On the other side, they're not. So that tells you the particles are coming from a single direction. And part of the spiral, the winds will be traveling roughly the same direction. Part of the spiral, they'll be traveling roughly in opposition. When that happens, you'll get like a 90-degree change, a complete 90-degree change in the direction of your magnetic field line. But Earth is getting just wave after wave after wave, and basically what you're seeing is outgoing waves meeting incoming waves. Now, there will be some resistance, especially if they're electrons, because electrons repel one another. So when you have a wave passing through the Earth and into the Earth's tailstream, you can see those arrows pointing back, looping around, pointing back, creating a V shape in those particles that are trying to exit and leave to the left-hand side. This simulation is looking down on the solar system, so you can see those spiraling whirlpools to the north and south of our tailstream are more like revolving doors. They're long, elongated. You're looking down on them. So that kind of tells you and the nature of the second wind is not that it's equatorial, but that it could be coming from north or south of the ecliptic. But you get that nice little V shape. That V shape progresses down and out and maintains its V shape as it exits the screen. Okay, that is not the focusing cone. Those are not arms or legs of a focusing cone where the sun or the Earth focuses cosmic rays, neutral rays into a focusing cone. Earth does have a focusing cone. You get to see it from time to time, but it doesn't move as a unit. And this one does, so that tells you we're ejecting electrons. And then it's followed by a second ejection of electrons. And basically, when you pack that many electrons into the equatorial region of our magnetic field, when you do that, sooner or later, they're going to repel one another and eject out. And not always into the tailstream. Sometimes they eject out at varying different directions, scattering out. So if you have all these particles that are running into each other and running through one another, you would have electron interactions. Electrons produce a huge array of radiation, from gamma to X-rays to visible light. Depending on temperature, change of direction, what particles they collide with. Are they colliding with a photon radiation? If they do, they can release gamma radiation. If they're colliding with a positron, it will release gamma radiation. Depending on what the electron does and the state and nature of that electron will also determine what kind of energy it's going to release. But if there's no spots on the sun and there's no flaring and we get just nice flat signatures on our graphs, you're pretty much measuring the background radiation around Earth. You're not even measuring the sun's radiation per se. Of course it affects the overall readings, but there's no spikes. So if you want a good idea of what the background radiation is doing, you compare last solar minimum X-rays to this solar minimum X-rays. We showed you where that purple and blue line, the most powerful of these X-rays, approaching gamma radiation, is tenfold. It's up from 10 to the minus 9 to above 10 to the minus 8, and it's staying there. So that tells me we have a pretty consistent medium right now, pretty consistent opposition. Now, if there was an object in the solar system, you could tell. I mean, if there was a binary twin with a very strong magnetic field, it would shape the nature of all the objects in the solar system. If a collision between that brown dwarf and a giant, massive, rocky, icy planet were to occur, you should be able to heliocentrically trace back the orbits of that debris to the source of the collision. And astronomers have done that and pretty much validated what was already written in clay tablets, that one big planet collided with another. In this case, it wasn't a planet. It was a very cool brown dwarf, sending it spinning wildly and very quickly, which creates a huge magnetic field. So look how the comets, the family of Jupiter comets, the Jupiter family, they all share common perihelion and very similar aphelions. They're their furthest point from the sun. Some of them are in more polar orbits, some of them are more ecliptic inclined, but they all overlap, which is what you would expect, a pattern you would expect from a Big Bang. They're all going to maintain their momentum. So it's funny when you map then the asteroid belt that you'll see that there's clusters of asteroids that favor one side of the solar system. And then when you compare the asteroids and the comets to just the planets and the dwarf planets, they too, OMG, they too favor one side of the solar system. Because of the position of those planets, they're trying to say that planet 9 is out to the right of the solar system. But yet, everything is tilted downward and stretched to the left-hand side of the solar system as you look at this map. These dwarf planets share common perihelion zones, as do the comets, as do some asteroids. All families of debris share a common point. And their perihelions way out in space, all occurring on the same side of the sun. That tells me planet 9 is nowhere out to the right. It tells me planet 9 must share the common perihelion, and the sandbox representation that we featured earlier this year was pretty darn accurate, and so was Robert Harrington's model. He was just the chief of naval astronomy, so his model was pretty damn accurate. Now, New Horizons went past Pluto, one of these dwarf planets, right? The largest of the dwarf planets. Pluto has moons. And when they turned around and shot the eclipse of Pluto on the sun, Pluto has an atmosphere. So not only does Pluto have seasons, has a moon, and has an atmosphere, has ice. Hey, it's not a planet. You know why? Because size matters. So when we have a wobble, we start to get polar opposite quakes. They don't have to be big quakes, but basically if you have a fault on one side of the Earth and then you tunnel through the Earth, and if you come out anywhere near a fault on the other side, those 2 points are being subjected to a change in motion, thereby stressing the fault line. If there was a wobble, the polar opposite of South New Zealand is South Spain. And we noticed this during the last wobble, that when New Zealand had an earthquake in the south, well, you know, how often does that happen where Spain has an earthquake too? So that tells me we're starting to wobble again. I cannot prove it because I cannot I don't have a setup any longer to monitor the North Star. Other people are going to have to monitor the North Star. The North Star wobbles, it's because we're wobbling. Now, why in the fact when this brown dwarf reached perihelion didn't it create a wobble? Why didn't it hurt us or kill us when it passed over the top of us? Well, first of all, it never came closer than the asteroid belt. So it never came inside the orbit of Mars. It stayed out by the orbit of Jupiter. And anything the size of Jupiter out by the orbit of Jupiter is going to look the same size. It's going to be another dot in the sky. But this one, being infrared only in its emittance, then would be harder to see because infrared does not fit into the visual light range of most human beings, unless you have an infrared scope or binoculars. So what happened, folks, was as this thing was close and passing over the top of us, it's both of its poles lying east and west on this planet, laying on its side, communicated with our poles, and one pole canceled out the other. So the magnetic connections, even though they were made, there was a cancellation, a wash of one pushing, one pulling, one pulling, one pushing on our north and south. As this thing ventures away, and as we pass in between it and the sun, we may lose contact with one of those poles that are pointing away from us now. As this thing ventures further away, its pole that's laying on its side and on the other side of the star loses contact with our pole, and now it can affect our magnetic field. It can affect our planet because there's not that cancellation of its opposite pole. So everywhere we look suggests that we passed between this brown dwarf like we told you we would. So when we vector out the alignments, it once again, it corresponds with other vectors we have drawn when there were earthquakes, clusters of earthquakes resembling a large body alignment, yet no alignments visible on the planetary diagram. The only alignments that are even visible are the fictitious ones, or the hypothetical ones, I should say, where we position the brown dwarf out, headed towards Uranus, headed towards the orbital ring of Saturn. So it's probably crossing over Saturn's orbital ring now, but its position is right where we thought it was. We're almost positive where this thing is. You know, there's a very low margin of error, but we wanted to erase that margin of error. So what I did is I went back and found a place that was tracking the movement of our magnetic pole. We saw throughout the last few months where the biggest deviations occurred. We had one in May, one in July, one in August that isn't shown here, and then one in September of last year when we said we were passing in between the brown dwarf. Listen, every time we thought we had an alignment with the brown dwarf, our poles shifted. Our magnetic poles shifted. And I'm sorry these don't show the dates. I guess some do. But we took and saw the largest flux of our magnetic field. We went back and looked at our videos and saw that we had earthquakes during that time, and that we had vectored our position with this brown dwarf and the sun at that time. At the exact same time they were registering huge fluxes in our magnetic pole, we were diagramming an alignment with a hypothetical brown dwarf. And they match up. They match up perfectly to our vectoring. When we had the earthquakes, guess what? We also had a magnetic shift. Now, we had other earthquake swarms associated with Jupiter alignment, Venus, la-di-da-di-da, without the magnetic signatures that we are seeing now. So what happened during this time frame where our magnetic fields took huge deviations and we had earthquakes? Well, at the same exact time, we were telling you we were in alignment with a highly magnetic object called Planet X. And the magnetosphere documentation of the actual drifting and movement of our magnetosphere absolutely corresponds with an alignment where we said that brown dwarf resided. And so this last vector showing Earth lining up with a fictitious object near the orbital ring of Saturn should be very, very accurate. If you're looking for this thing with your infrared, there you go. You're looking, it's not quite reaching Uranus, and this thing may pass directly over the top of Uranus. So look for changes in Uranus. We've already had changes in Uranus. Look for additional changes. Until next time, be prepared, not scared. I mean, and there it is, guys. We proved it. Our earthquake alignments, our vectoring, happened to fall on the same days as our magnetosphere was going crazy in terms of its position and orientation. Imagine that. Higher truth. We're right again. But it doesn't take a genius. It just takes diligence.